In this video, I'm going to talk a little bit about regressions. I forgot to start streaming on Monday, so I want to make sure you guys have the content covered in video form in case that helps someone prepare and study for the exam, because a few of you mentioned that you thought it would be helpful to you. In this first video, we're going to talk about a regression equation. This is the basic form that linear regression takes. Other kinds of regression take variants or slight modifications of this form, but this is generally speaking how it's going to look. What have we got here? We've got a target. This is the thing we're trying to predict. We've got a bunch of features or factors. I'm calling them predictors here. These are the columns in our tables, so passenger class or sex or age. Attached to those predictors are a weight, also known as a beta weight or a coefficient. These are some measure of how important that feature is and in what direction that feature points. So if we're trying to regress for the Titanic, predict whether a passenger survived or not, we know our target is going to roughly vary between 0 and 1, and we're going to have a cutoff or a threshold that we put somewhere in there that'll determine what's survived, what's died. But it's somewhere between 0 and 1. We know that some things contribute more than others. For example, we know that passenger class is a pretty decent predictor. So that means that the weight on it is going to wind up being fairly big. So the number will be closer to 1, 1 being the difference between 0 and 1. So it's closer to taking up the whole range as opposed to taking up almost nothing. The other big thing that we get out of it is we know that passenger class, as passenger class gets higher, so if you go from first class to second class, or second to third, the number 1, 2, 3 is going up, your chance of survival goes down. So that means that the weight on passenger class is going to be negative, because as passenger class goes up, it should hurt you more and more. Finally, I want to talk about this intercept a little bit. This intercept is what your prediction would be if everything else was 0. That doesn't always make sense. You're going to have plenty of times where a 0 is unreasonable. So who is in passenger class 0? How many, if we were trying to predict whether people got in car accidents and used their age in a feature, how many drivers are age 0? If we're talking about likelihood of winning the lottery, there's not a lot of people who buy 0 lottery tickets that wind up winning. So it isn't always sensible to interpret an intercept as meaning much of anything, but it's in there to make the math work better. And sometimes, depending on how you code your variables, which will be a little bit later, you can make it mean something meaningful. Now that we've gone over what the parts of the regression equation, of a linear regression equation are, I wanted to walk through how you use it. This is the kind of thing that could be on an exam. So I have given you, for purposes of this question, the regression equation is this right here. So our intercept is 0.84. We are multiplying p class by negative 0.2. We are multiplying age by negative 0.01. And we are multiplying sex by 0.48. We're using that in order to predict whether someone survived or not. For our first row in here that represents a hypothetical passenger, we would have a formula that looks like this. 0.84, because that's the intercept that everybody gets, minus 0.2 times 1, because they're in first class, minus 0.01 times 45, because their age is 45, plus 0.48 times 1, because their sex is 1. What does sex equals 1 mean? We'll talk about that when we get to coding. For now, just accept that we put a number in there. When we add all of these together, we are going to get 0.67. So our regression equation is given a value of 0.67 for the prediction of whether this passenger would survive or not. Now we're going to look at the second row. This passenger gets the same intercept because everyone gets the same intercept. They have the same p-class, so they get the same p-class. They're 25 years younger, their age is smaller, so we're subtracting less. But their sex is also smaller, in the sense that it is 0 instead of 1, so they aren't getting this bonus. Together, this leads to 0.44 as our prediction. The thing worth looking at here is, yes, this person is less likely to survive. That's the most important thing. But we had right here going from 45 to 20. Once you include the weight, that gives us a difference of 0.2. So they are 0.2 better off in terms of surviving based on their age. I'm sorry, 0.25 better off based on their age. However, they are 0.48 worse off because of their sex. The difference between the two of those is enough that it gives them a smaller chance of surviving overall. When we look at passenger 3, we get the same 0.67 that we got from passenger 1, despite them being different. How did we wind up with the same prediction there? Well, we plugged everything in, just like before. But this time, age is 40 lower. So we get 0.4 better off based on age. But P-class is 2 higher, so we get 0.4 worse off as a result of that. The 0.4 and the 0.4 offset each other, so now we've got the same prediction. Why does this matter? Well, aside from being required to plug in stuff like this on an exam, this matters because you're able to see how much different factors matter. So the feature importances that we're getting out of data robots come from these sorts of weights. We can get how important they are relative to one another based on how what the absolute value of that number is. And we can get whether it helps or hurts your chances based on the sign associated with the weight. It also means that we have ways that we can figure out how to make business recommendations for how to manipulate the data in the future. So we could, if we knew that home prices, if we knew that having a high crime rate in the neighborhood was bad, and that hurt your score, or how much you're going to sell the house by 300 grand, you could say, well, what else could I easily change in order to get that 300 grand back? You're not going to be able to change what school district it's in. You won't be able to change whether they have access to high-speed internet, but you might be able to change whether they have a finished basement. Well, then you could go and look up in your list of coefficients, does having a finished basement offset the 300 for the neighborhood going downhill? And then you can piece together other things like that in order to find ways that you could manipulate things to increase your odds. So that's part of why why it's good to have these regression equations handy when making a business case to someone.